Hello. Okay, let's start. Today we will talk about the linear regression algorithm. And if we hurry up, I hope we will discuss the car-neighbor classifier at the end of this seminar. I suggest a little draw at the beginning. And I hope that we remind some theory, and then we will consider the notebook. I suggest to consider for simple case this algorithm. In real life, we work with more complex situation, but for our lesson and for uh, more simple understanding, it will be enough. The most popular task for linear regression is predicting of price on real estate. If we will formulate a common task is just find the function which maps our x space with the space of our target. And for example, you have a real estate and you want to predict the price of your real estate. For example, you have only one features, and your features is size of your real estates. Size, price, for example, I don't know, 100 meters squared, 30 meters squared, 60, and etc. And we can write the price, $1,000, and $700. It's your data set. It's your data where you have features and you have a target for your features. We told previous lesson that usually you have a train data set and test data set where you check your model. Usually you have a validation data set, but in the classical task with sklearn, we use train and test data set. So this is a piece of your train data set. You can write the model function for your task, and it's weight 0 plus weight 1 x, where weight 0 and weight 1, it's your parameter which you want to get at the end of learning, and x is your features, it's size of your real estate. If you remember, I hope you remember that when you was at school, you worked with in geometry. You worked with plane and line, and the equal of this line you wrote like kx plus b, whereas the k is coefficient responsible for slope of your line, and coefficient b responsible for shift your line along the y axis. So it really it's the same equal, but for other task. But we can consider it just like some line in space, and this line will describe your real estate. In real life, you work with many features, and you have BS weight 0 plus weight 1 x1 plus x2 and etc. But how I said, we will consider simple case because all statement leave the same. When you have the model and equal for your task, you want to appreciate and your model and understand the accuracy. Um, can you get precisely result if you will use this model? And you want to calculate just error. You have your y, its value which was predicted your model, and you have real value at target from your dataset. And this you want to calculate this error. And now uh, we can consider two function with helping which we can estimate our model. It's Maye and MS. Yeah. You have error. It's your E. You have apps. It's your A and squared. Sorry. And you have mean. That means you just sum of for all samples in your dataset and calculate mean value, where n is a number of sample in your dataset. Also, we can consider RMSEM. Tell me, please, which problem did this function? You calculate error and use squared. What's the problem? For estimating your model.
It doesn't tell us if it's more or less, it just tells us that there is error. It doesn't tell us what direction the error is in.
Okay. So when you want to appreciate your model, you want to get result in scale of your data. But when we use squared, you get more, you have the bigger result, and you won't fix it. So you have one matrix for linear regression task, and it's RMSE. You just take MSE and yep, root for this value. To be honest, in linear regression task, we can use R² metrics, and it's also the good metric. But as I remember, we will consider it at the end of the seminar. Do you understand it? I think it's simple, but maybe you have a question. Okay, let's try to see our notebook. We will generate synthetic data, and we want to discover behavior of linear regression algorithm, and we will consider regularization problem, and next step consider gradient descent method and stochastic gradient descent. Okay, we will generate our data. We will use n features, 2 features, an object, 300, and we want to modeling weights true from normal distribution, and also generate our features from uniform distribution. In this line, we will scaling our features for what? Let's draw. When you solve the real problem, you have the features in different scale, and you have, for example, okay, you have a price, and price belong, well, for example, $1,000 to $100,000. But if you want to consider, I don't know, for example, num of bathroom in your real estate, this number belongs, I don't know, 1 to maybe 5. I don't. I have never been. I have never seen real estate with more than 5 bathroom. So I think it's normal. You see that it's a really different scale, and when we generate our data, we want to use this information and some scaling our features. And we like x multiply weights true, and we generate our target. So let's try to yeah. You have seen that shape of your weights massive is 2. You have 2 weights. You have 300 your sample, and you have 300 targets for your samples. MSEM, mean square error, we discussed it. And also when you solve linear regression problem and use linear regression algorithm, you can get your solution with helping two methods. The first method, it's analytical solution, and this solution, which you can see on the my screen. I want to show the output of this solution, but I think if you want, I can send materials for geometric output and algebra output. So uh, also, maybe from lecture, you know that about Gauss-Markov theorem, with helping you also can get this solution. And sometimes when we have a few data, it's really good solution because you can know that with this expression you get the optimal solution for your task, for your weight. You have matrices of your features transposed, multiply on this matrix, take inverse, multiply on X transpose, and multiply on target in your training dataset. And you get your weights. But tell me why these methods work worse when we have lots of features and lots of data. Why it could be bad?
The inverse might not. With the matrix is square.
Repeat, please.
Is the matrix square?
Yes. When this operation, inverse matrix, it's really complex operation. And when you have lots of data, you just you get very, very slowly algorithm. So you need to more practically methods. But if you have a few features, it could be work. But um, let's try to calculate this expression. You use generating X and target. And when we have two features, you can see that result generating weights and calculating weights and true weights which we generated. It's the more closely enough. But let's try to use correlated features. Do you know about correlated features? When we can, for example, when you can features x1 and value 1, 2, 3, and you have feature 2, and this value 2, 4, and 6. You just take first features, multiply on 2, and you get 2 features. And it's linear dependency. your model don't get the new information when you use two such correlation features. You want to your features will be independent. But what happened if our features is correlated? Let's take three features, generate weights true, matrices X from uniform distribution, but let's fix our third features. You get your X massive matrix and fix third features and told that you take the second feature and add some noise. The epsilon it's a very little number. So you get that your third feature it second feature with some noise. And to be honest, it's really bad, but we can understand why. Let's try to calculate our data. This our calculating weight, and this our true weights. We see that first feature really close, but what happened with third and second features? It's something something strange. Let's change some noise. Sorry. If you will change your noise value, you will get every time the different value for your weight. And it's really bad situation. Do you understand why? When we considered our analytical solution, we wanted to get one optimal solution. And now we in situation when we have infinity combinations of our second and third features, which in sum will be closely or true. And we want to fix it, some methods. And now we can consider the regularization term. But tell me, do you understand what's the problem? What's the problem in correlating features? Do you see that we can get infinity combination with true sum? Or you have a question? Okay. No question, silence. I hope that you understand it, but I can repeat this information. In this case, you get values, our weights, very exactly. And it was very close to true weights. But in this situation, we every time reloading our program will get different values, but in sum it will be closely to real weights. And we in situation when model understand the common direction learning your model, but it can't to understand how distribute weights between third and second features. Model can't to understand proportion between second and third weights, features, and don't understand which features more important for this task. And we want to fix it with regularization. You have L1 and L2 norm for regularization, and as I remember, we have some regularization function for with the sum of L1 and L2. But to understand it, let's write the loss function and cost function, or cost function. It sometimes called loss function, sometimes cost function. We said that MSE is this expression. And you want to define which function you will optimizate, because when we talk about possible solution for this task, we said that we have analytical solution, but it's not always good. And we want to find the something, some other solution which can help to solve our problem. And this solution usually called iterative methods, and these methods use the gradient descent approach and other gradient approaches. And we want to let's say that this expression is our cost function. To to understand it, you remember that your predicted value, it's just y weight x, where weight 0 plus weight 1 multiply x. And your cost function, it's just this expression. You want to find the minimum. This function you want to minimize. This function to weights, because you want to find weights with which your error will be minimal. And what about regularization? We we are considering cost function, and with the cost function, you can add some penalty. Well, let's write this ms here with L1, L1, sorry, and ms here plus L2. The L1 is sum of your sample this expression, it's just sum of your weights. And L2, sorry, without coefficient. Squared your weights. And when you add in your loss function some such penalty, you force your function make a penalty for the high weights. You just make a border for your weights and make it make your model more stable. And in this expression, it's our analytical solution. We can add a regularization penalty to fix the next problem. If you have correlation features, your X transpose X matrices could be close to singularity. Why? Because when you calculate these matrices, these matrices, you use determinant, these matrices, and some other expression. And when you calculate determinant of these matrices, if you have collinear features, you get that determinant is 0. And when you will calculate inverse matrices, these inverse matrices, you just get 0 in denominator, and it's the bad situation when we can't to work. And the regularization part can help to fix it because, for example, lambda is a hyperparameter. You just take your matrices and add some part. How it can help? If this one it's such matrices diagonal matrices with one on diagonal. And when you understand that your matrices are close to singularity matrices, you, for example, 1, 2, 3, I don't know, 2, 4, 4, and it's some collinear features, and mm, you can write it this. And when you add these matrices, you get that on diagonal +1, and it helps to fix situation with 0 determinant. And when you will calculate determinant, it will some possible value, and we will fix the problem with singularity matrices. Do you understand how it works? How it works? Sorry.
Yes.
Perfect. Let's try to see how it works in code. It's your regularization part. You have lambda coefficient and I matrices with I. We also use our collinear features from this generating part of our code. But with regularization, we get more close result from true weights. And also we can check the sum also close to true weight. Okay, now we can discuss the gradient descent method. Let's try to draw. We will consider a situation with a simple function 0 plus x. If you let's imagine that this 0 and it's just a line from 0. You remember the cost function, which likes like MSE, and cost function is squared. It could draw like a parabola, and parabola have some minimum, global minimum. And when we calculate our error, we want to go to minimum in our function. If you have one features, yes, and this your function. But if you have more features, it more problematically draw in, but we try. For example, we have 3 dimension, and you, sorry, this not features is your weight one, and you want to draw how could seems your function in 3-dimensional space. I think it's some this, and you see dependency from weight 0 and weight 1. And this function, you can draw some contours of level on this function, and your optimal value with the minimal values of error, it's this point. And you want to go from this, you want to go to this point, but you can start from random point, for example, from this or from this, and your task is it's moving too close to your point. Tell me, please, what is the gradient vector? What it shows for us? When you have some function, for example, f, x, y, z, uh, which the gradient vector for this function? And which mind?
It's the partial derivative of f with respect to x, y, and z.
Um, it's vector of partial derivative for your function. And which mind of gradient vector? If we speak about function behavior.
Can you repeat again? What was the question?
You have behavior of your function, for example, this, and you calculate gradient vector in some point. Which direction to show your gradient vector?
It gives the direction of the maximum change of rate. Like,
Yes, direction maximum to maximum grow your function. But our goal now, it's go to minimum function. So you can just calculate the gradient and then write minus your gradient vector. And we will get the direction of minimize your function. So we want to update our weight, values of our weight, next expression. We take our weight and write for gradient for cost function. Why gradient with the weights? Because your cost function depends on your weights, and to minimize your loss function, you can change your weights, and so you change weights and you take derivative with your weights, and also we have some coefficient. It called learning rate, and learning rate show size of step with the moving among the function. What I mean, you can in two-dimensional space. For example, you start from this point, and you can make baby step, very, very little step. It really slowly, but you can probably endure to come to minimum. But you can start from this point and, for example, make size more for your step. For example, this and this. You're moving faster, but you can um, go out from minimal point for your function. And analogical in this situation, you start from this point and you need to define size of your step. Okay, it how works the gradient descent. And let's try to see how it work in code. Oh, yep. Important thing. If we want to calculate gradient, our cost function is this value. It will looks like this expression. But if you want to check it, you need to read more about matrices operations. I think I will send you materials from this. Now we use our example with two features with 300 objects. Num steps in gradient descent is number of iteration in your algorithm, and batch size it for stochastic gradient descent it will belong. Generate our data. And in this code, you realize expression for calculating your gradient. We start from random weights. We can start from random weights. We can start from 0 weights. But in this code, you start from random. And yeah, make iteration for learning your model. Let's try to show it. This this image show this image it the same, but for this case it's three-dimensional space, but your y values on this part of your graph. And this is starting point for your weights. You can sum value for weight 1. You can sum value for weight 2. And you make iteration and try to select the optimal weights for solving your problem. Tell me, please, why the behavior of this line very broken? Why it's not smooth? Why it's very broken? When we consider the gradient vector, it vector which orthogonal to equipotential lines. Equipotential lines, it's these lines. In our cases, it's ellipses, and our gradient vector orthogonal to our ellipse. This ellipse means that our function it constant on this ellipse, and gradient vector to yeah, orthogonal to these lines. Okay, let's show some other interpretation, anti-gradient demonstration. Yeah, so when we speak about gradient vectors, anti-gradient, it's gradient with minus in expression. And you have vector space, and you have direction of changes your function for this space. What's the difference between stochastic gradient descent and the usual gradient descent? When we work with gradient descent, we use all training data. When we work with stochastic gradient descent, we use only some batch of your data. It's very it's a few samples from your data. For example, you tell that batch size equal 10, and on every iteration, you choose 10 random sample from your training dataset and use it for updating your weights. It's less computationals than in gradient descent, but you can get the experiment to check which method will use in your task. And let's to run stochastic gradient, you choose batch size 10, and when you take samples on every iteration, you can see that we choose only batch size numbers from your data set. And also you can calculate your gradient and updating your weights. Yeah, it's stochastic gradient descent trajectory, but what's the problem? In these methods, problem in convergency, and you want you want to convergency in minimal point of your function, but the random character of this method, it can be bad for this task. And so this reason we need to use some rules for choosing size of step when you learning your model. These rules called Robin-Monroe conditions, and what it means. You have two conditions, and the simple explanation, your step must be big enough, but not too big. And you talk that some of your step size divergency, but squared sum convergency, and some conditions which helps to define and control your step size on the every iteration. And it's some automatically changes your step for learning model. It's really important things. Yeah, at the same time, it should diverge not so fast. You need to define step size to convergency in minimal point of your function. Let's build stochastic gradient method. Where is our Robbins-Monroe condition? It this, and you can check that this sequence to convergency, but I don't like these things, and I leave it for you. And now we can see that stochastic gradient descent trajectory become more stable and more convergency. Okay, the important things from linear regression algorithm is condition number. Do you know about condition number? Okay, let's discuss some information about condition number. Maybe you remember that any matrices we can decompose it with helping singular decomposition. If we have, for example, matrix A, you can decompose it is like this expression. As I remember, this and this matrix is orthogonal, and this matrix is diagonal. And in these matrices, on diagonal, you can find singular values for these matrices. Singular values in some mind close to principal component method because they show features with the with maximal variance, and you can define you can help to define features with which more important for our model. And you need to choose from these matrices the maximum singularity value and the minimal singularity value. And this maximum and minimum value can help to define condition number. What is condition number and what it means? Condition number, it's a value which helps to define stability our model. If we can multi-collinear features, some little changes in our data can lead to very big changes in our result and in our weights. And if condition number is very big, it means that our model unstable. If it number little enough, you can talk that your model is stable. Let's check. We can free function. This function describe the classical gradient descent. This function describe stochastic gradient descent. And yeah, function describe RMS here. We discussed what is it. We have some noise. And let's run our cells. I want to show you some graphs, yeah, with the dependency singular value and condition number to noise. Sorry, I don't understand why I change my Google Colab. Okay. When you add some noise to your features, you understand that if you have the second feature, how it example above, and to second feature you get you add some noise and talk that it new features, it bad situation. But if you add more noise and more enough for enough difference between the second and third features, you get more. You get sorry, better result. And you can see that if we add noise on every iteration, our condition number decrease. And when condition number decrease, we understand that our model become more stable, because you if you use analytical solution, we discussed that collinearity of our features get some bad results. And if we add more noise and these features become more different, your condition number decrease, and it means that your model become stable. If we look to gradient solution, we can see that our collinear features don't influence on learning model. This part, it's just other data you add in your data training, other data with very big noise, and your model just need to rebuild and relearning with for this data. But if noise very little, you see that your solution stable enough. And in the gradient, sorry for yeah, stochastic gradient method, you get solution which doesn't depend on collinearity features, because you on every iteration take really random and different part of your data training, and because of this random, your solution and your model more stable, and the collinear features don't influence on result. Yeah, below you can see the classical realization linear regression in sklearn. I will not stop on this part, because it's just using ready algorithm, but you can see that if you can linear regression, and you can reach linear regression, it's linear regression with regularization function. And if we talk about uh, methods for getting solution in linear regression realization, use analytical solution. In this realization reach, you can use different iterative methods, and you see that solution without iterative methods, it 8.4 second, and solution with some gradient method, it's 1.5 second, and it's really better with time. Yeah, in example below, you generate some data, and you use linear regression that stochastic gradient descent. You see some mistakes, because our features is because our features have really bigger values, and in part below you want to use standard scalar transformation for scaling these features, and fix this mistake for stochastic gradient method. At the end of this notebook, I add some useful links on Kaggle notebook. You can see it in materials which I will send after our seminar. But it's a really cool notebook, because in their realization use real data, for example, house pricing data, house prices data, sorry, data, and you can see how could look like data, which features could be, and it's really useful information for creating your understanding for machine learning problem. And also, if we speak about famous task in regression algorithm, you also can check part code on the Kaggle, and learning some popular code, because often you can get really useful information for you, maybe some interesting approaches, some interesting methods, and etc. And I recommended exactly learning this links, and other links if you interesting it. We can 20 minutes. We have 20 minutes, and I think that you can speak about K-neighbor classifier, because I promise you. Okay, let's run. We finished the part with the linear regression algorithm, but in our course we will consider different approach for solving regression problem. But in set of algorithm in machine learning sphere, you can choose a few algorithms, very simple, but very useful for your tasks. And k-near neighbors, it methods which that you can use for classification problem usually, but also in some cases you can use it for solving regression problem. Let's where is my Miro? Okay, yes. K-near neighbors. How it works? How we can classify object with these methods? Let's imagine that you have three labels in your dataset: triangles, squared, and circle. You have three classes. And now appears some mysterious object, and you want to define which class this object belongs. How you can do it? How it do it k-near neighbors? You I taught in previous lecture, but this method you can characterize this statement. Tell me who is your friend, and I tell you who are you. Because of this, you will see near object in for your mysterious object, and you will calculate some metrics. Usually, it distance from your object to every object in your dataset. And for example, you can calculate Euclidean distance or Manhattan distance, and if you some distance, and you need to take every data point in your dataset and calculate distance between your object, for example, A, and object B. And next step, you need to create massif, and this is D1, this is D2, D3, and you add your D and sort that D1 more than D2, D2 more than D3, and D3 n more than equal to 0, because we calculate distance, and it must be positive. And when you have sorted list of your distances, you need to choose k near distances. K is this k. It's some number which describes how much distances you considering. And in our case, we consider 3k. We think that k equal 3. And you next step, you need to look in this free distance. For example, this squared, and this circle. And you see that you have 2 squared. Maybe your mysterious object is squared. But if you consider this situation, d2, d3, d4, d5, and the situation is that d1 is squared, circle, but d4 and d5, it's squared and squared. And your k equal 5. And in this situation, you will considering your mysterious object like sorry, not squared, circle. In this situation, you will consider your mysterious object like circle, because you increase number of neighbors, and you see only 5 neighbors, not 3. And for 5 neighbors, your object suggesting circle. And your k, it's hyperparameter. Usually in experiment, you try k, I don't know, I think 120 maybe, but 1, it's really little, because if you see only one neighbor, it can be non-representative. But I don't know, maybe optimal 5 or 7. But I know that you have empirical rules that you can consider k like n root from n. There is n is amount of your data sample, so you can check it. Which important things I need to say about k-neighbors classifier? Okay, I remember, but let's check what happened in our code. You work with toy dataset. You modeling data with make classification, samples 100. You have 2 features, 3 classes, and let's try to get the image with distribution our data. You see that we have 3 cluster of your data, and purple, blue, and red. And you want that when appears new object from that in training dataset, you haven't this object. It's new object for us. And you want to calculate distance for this object to this, and every data point, and define which class for your new object. Okay, you split your data set on training and test data. Call neighbors classifier. And get the predictions. You can visualize results with different value that different amount to neighbors, and notice how changes your accuracy metrics. For example, is 1 neighbors, 2 neighbors, 3 neighbors. Yep. 10 neighbors, 20, 30. And you can see how changes your dividing your classes. It seems really good because 0.87 it's really good metrics, and in previous cases we got metrics more. But what happened? What will happen if we increase amount of our features and run our algorithm, and we have 0.6. It's really bad metrics. What's the problem? How do you think? We considered that neighbors classifier calculate the distance between object. So if we use, for example, object A and object B, and we know that for object A we have 1, 2, 3, 4 vectors, and for object B we have 25, 30, 1, and 0 vector. And when you calculate distance, you get the sum of difference between this and this value, this and this value, this and this, and so on. And what's the problem? How do you think? If we can, if we have really lots of features, why neighbors classifier can work worse?
It's computationally expensive.
Yep. It's really expensive, but the main problem is проклятие размерности. Curse of dimensionality. Yeah. When you do you know about problem with watermelon in high dimensional space?
The distance between points become less meaningful in high dimensional spaces.
Yeah. And in high dimensional spaces, for watermelon, red part is decrease, but green part increase. And in very high dimensional space, you can't eat your watermelon because it's only green part. And if we make analogy to k-nearest neighbor classifier, when you go to high dimensional space, all information moving to border, and you get that your features near your data point, your samples near and far become really close, because in high dimensional your near neighbors and your far neighbors, it's very similar, it's really similar values, and classifier work bad enough because you're calculating for samples data become very similar for near and for far samples, and all your samples kind of border of your high dimensional space, and you get very difficult computational complexity, and it doesn't work. Okay. On this graph, you can see how decrease our accuracy metric if we increase amount of features. You consider 1 second. Yeah, dimensions and classes, 5 classes. And you consider cases with 10 features, 20 features, 50 features, and you see that with 10 or 20 features, no, I think only 10, only 10, you get enough accuracy, but if we will consider 1000 features, it's really close to random result. I think we finished. If you have a questions, I'm ready. If you don't have the questions, thank you for this lesson. Okay. Good evening. Goodbye.